Okay, so like I said earlier, so based on the feedback from my mid-semester survey, which I got 20 responses on, which is what I wanted. So now this 20 has gone down to 15 Smarties. So only 7 more Smarties needed for me to Venmo everyone to attend the section, the unit cost of an Oreo. So what was I? Yeah. So I got some feedback saying that we should start class a little bit earlier, and my apologies. I realized that class ends at like 50 minutes and not 55 minutes. I thought it was 05:55, but it's actually on sharp to like 50. So we'll start. Let's still give people a little time to filter in. So we'll start at like 2 minutes after the hour from now on. So just keep that in mind starting next week. My apologies for that. So y'all can see my board, right, on Zoom? I think that looks good. Okay, so today we're going to do exam review for exam 2. So I think what we're going to do is we're going to try to do both of the dynamic programming problems, and we're going to do one of the network flow problems. So we're going to start with the network flow problem because I think people want to focus on that a little bit. So let's take a look at problem number. They're not numbered, but it's a problem that literally says network flow. So I'll draw the graph here, and while I'm doing that, yeah, try to figure out like parts 1 to whatever you can, I guess, and we'll see how much time we need for that.
What did it say?
Sorry?
The network flow?
Yeah, number, yeah, just the one that says network flow on it. So again, we're doing the exam prep problem that says network flow. Okay. Okay, so let's practice running the 4-12% algorithm on this. Okay, so I've drawn the graph over here. So which path do you want to relax first, or which path do you want to follow first? You can really choose any one. So any suggestions?
749.
Yeah, sure. We'll relax the 749 path. So the first, let's remember what we're doing. So first we're relaxing the path S to A, C, T. And so what happens to the 7? Right, okay. So we reduce the 7 by 4. And we get 3. And what else do we have to do here?
4 backwards.
Okay. Okay. remember there are two steps to every edge relaxation along the path in forward 12%. You decrease the capacity of the forward edge by the desired amount, and you add that same capacity to the backwards edge along that direction. I think there's a question in chat. Hang on. What is the weight from A to D? That's 2. So this same diagram can be found on the discussion worksheet on the outside. So this is 2. Right, it's a bit bigger. Okay, so right, so we've subtracted 4 from 7, and then we've added 4 in the opposite direction. Subtracting 4 from this over here, right? Well, that just makes it 0, right? So this edge gets destroyed, and instead, get an edge going backwards. Okay, so maybe so the forward edge now becomes a backward edge because you like subtract 4 from the capacity, and then you add a reverse edge of value 4. And so this 9 similarly becomes a 5. And again, you add a 4 backwards. Okay, so we've destroyed the path S to A to C to T. Okay, what next? When do S, B, dt? Okay, and so what is the maximum we can do here? 3, right? Okay, by the way, this is a plus 4. We got a plus 4 out of this one. We're going to get a plus 3 out of S to B to D. Okay. So 6 becomes 3, right? I'm going a little bit fast because at this point we should be familiar with it, but I want me to slow down suddenly. 3 forwards because 6 minus 3 is 3, and then 3 backwards. This 3 is the kind of like cutoff edge. By the way, you should notice that like this, we did 4 of this because this edge was that kind of some kind of cutoff, right? It was some kind of restricting factor. Huh? It's a bottleneck. It's a bottleneck edge. I'm alluding to what we're going to do in the rest of the problem. Okay. So this 3, right, becomes 0, and we flip the direction. We add like this 3 gets destroyed, and 3 comes in the opposite direction. Okay, and then what happens to the 5 over here? 5 becomes 1. Yes, 2. Or yeah. Oh yeah, yeah, no, it's all good. Yeah, so 5 becomes a 2, and then in the reverse direction. Okay, so we're done with this path, and we've destroyed S to B to D to T. So what path still exists? Well, can anyone name one? SADT. So what can we do along SADT? What is the limiting? 3, 2, 2. So we can only do 2. S to what did I do again? A to D. Okay. What happens to 3? Yes. Right? Because we're subtracting the 2 from everything here. And remember, instead of adding like another parallel edge of weight 2, we could just change this 4 to a plus 2, so we get 6. This 2 again, in some sense, is the bottleneck. Okay. So now we get a 2 backwards because we destroyed the 2 forward and added a 2 backwards. And the same thing over here, we destroy this 2 over here. And in its place, we change this 3 to a 5. Okay? All right, so now we're done with that path. What paths remain? Do any paths remain here?
S to C to.
S to B to C to T. And how much can we do? 3, 2, 5. So we can do 2. Three becomes a 1. This 3 becomes a 5. this 2 changes direction. This 5 becomes a 3. This 4 becomes, wait, no, where is it? This 4 becomes a 6, pardon me. Okay? So, what is the value? So, do we have any paths left? Well, no, because A is stuck, that can only go to S, so we have to go through B, but B can also go only to S. So, there is no paths from X to D. Okay? So, what is the value of the max flow here? Well, we just add these up, right? Plus 4, plus 3, plus 2, plus 2. What is that? 7 plus 4 is 11. Okay? By the way, you should check this because remember these outgoing edges were not there in the original graph. They have been added in the residual due to 4-12%. And it's no coincidence that 6 plus 5 is equal to 11. Okay? It's the same as 4 plus 3 plus 2 plus 2. Similarly, right, this source had nothing coming into it because it's a source, but now it has 6 and then 5 coming into it. Again, 6 plus 5 is 11. Okay? No, there's like, yeah, as Master Uguay said, right, there are no accidents, right? So this is a very specific reason this is happening. Okay, so yeah, I mean, any questions about running 4-12% on this? Okay, so we need to find a minimum cut. How can we find a minimum cut? I should have drawn a second copy of the graph. Okay, while I do that, try to work on the rest of the problem. Okay, so we'll find a minimum cut shortly. Okay, yeah, so I've drawn the graph. Let's try to find the minimum cut. The minimum cut, we know what value the minimum cut should have. 11. It should be a value 11, right? By the max flow min cut theorem, the max flow is equal to the min cut. So as long as we find any cut of value 11, we're done. Could there be multiple graphs? Could there be multiple cuts in a graph with like the same value? Is that possible? Yeah, sure. There could be multiple min cuts. Just like there's multiple ways to pump max flow. Okay, you should think of every way of pumping max flow is associated with the min cut. There's a very theoretical reason for that. And if you're more interested, you can see me in office hours. But it's something called duality. The reason that max flow corresponds to min cut. And if you learn something called linear programming, it's actually a very beautiful kind of relation between these two kinds of things. But anyways, I'm not going to go on any longer on that. So we need to find a cut of value 11. Any suggestions? Down the middle. Down the middle, exactly. I get a chance to do this now. Okay. So this cut has value. Can you see that on the? Try to see if you can see that on the Zoom. I mean, it's one thing to look cool, but okay, it doesn't show up that well. I'll just. Okay, so this is the cut. See, this is a lot lamer, but at least you can see it, right? Can those of you on Zoom see it? Okay, cool. Yeah, so this has value 11. Okay, so that's the min cut. There can't be a cut that's smaller, otherwise the max flow is small. There might be another one that has value 11. I don't see one off the top of my head, but there's nothing that really excludes that from this. Okay, so why is this the minimum cut? No, like this 4, there's a 4 here, there's a 3 here, there's a 3 here. There's a 2 here, 2 here, 2 here, 2 here, right? That's kind of interesting that it happened that way. Like, again, is that a coincidence? No, okay? What's special about these edges? Well, you notice that each one of these edges is now facing backwards, right? There was an edge there before, but now it's the same edge facing like backwards, okay? Why is it facing backwards? Why is there no forward edge? Well, it's because that is the restricting edge along each of the paths we relax, right? For S to A to C to T, we chose to pump 4 units of flow because 7, 4, 9, okay, so 4 was the maximum we could pump without breaking any pipe, okay? So that's what it means to be a bottleneck edge. And so the minimum cut, right? The minimum cut is comprised seemingly exactly of these bottleneck edges. Does that make sense? Okay, so how would you increase the maximum flow in a ground? What would you also have to increase? Yeah, but more specifically, you have to increase the weight of an edge in in the min cut. Exactly. Is that always true? That well, you have to increase the value of the min cut to increase the value of the max flow. Okay, so we're working on we've moved on implicitly to part like 3 now. What's part 3? Part 3 is okay. List all bottleneck edges. Then if you increase it, do you increase the max flow? Well, you realize that if this 4 was a 5, then we could have pumped 5 units of flow along this. If this 2 was a 3, we could have pumped or well, let's say it's like 2.5 or something. You could have pumped more units of flow along this path. If this was like 2, if this 2 was a 3, we would have pumped more flow along this path. If this 3 was like a 4, we could have pumped more along this path, and so on. Okay. If we increase any one of these edges, you should confirm that the max flow also increases. Whereas increasing this over here doesn't really do anything for us, right? Because in this graph, in the final residual graph, we still have the capability to send more. Okay? But yeah, I mean, is there another edge that's like a backwards edge now that was a forward edge before? Well, this one over here is. But is this thing over here? If we increase that and nothing else, would that increase the value of the max flow? If this 5 became a 6, would this increase the value of the max flow?
Not by itself,
Not by itself. Why not?
because the 2 and the 3 are so small edges and very flat, very close.
Right. If it comes into D, it has to go through this 2-weight edge or this 3-weight edge, which I mean, only 5 units can come in, so it doesn't matter what this is. Might as well just let it be equal to 5. Okay, so increasing that does not increase the max flow because the inflow into D is constrained by some other edges, which so happen to be bottleneck edges. So bottleneck edges are these ones over here, and they correspond exactly to the minimum cut.
But isn't there another minimum cut if you go like 4 to 5 diagonally?
Like 4.
To yeah, that's the bottom 6, that one, and then the 5. Like you go diagonally from the 5 to the 4, that also equals 11.
But is it a cut?
I'm not sure.
Remember, so a cut is defined by
Yeah, it is. It has a T on one and then an S on the other. So like you go diagonally from the 4.
like this.
No, the other way. So like from the 4 to the 5,
Oh, I see.
like that.
Huh. Yes, you're right. You're right. So, very good point. So, what I failed to realize here, actually, this 4 is not a bottleneck edge. Is it a bottleneck edge? Okay, so if we increase the 4 to 5, what happens? If I'm 5 units of flow that way, but oh no, this okay, no, this 4 is fine. This 2 is this 2 a bottleneck edge? Yeah, okay, so I made a mistake. Okay, so this 2 over here is not a bottleneck edge. This 2 is not a bottleneck edge. Why? What happens if this 2 becomes a 3? Then you might say we can pump 3 units of flow along this, right? But then this goes from 4 down to 2, and then we can't use the full capacity of this, if that makes sense. So we're still constrained by this 5 over here. Okay, there's 5 outflow from here. So increasing this from 2 to 3 doesn't really do anything. Now, if this 2 was a 1, then we could increase it to 2, because then 5 inflow and then 5 outflow. But this 2 is not a bottleneck edge. Okay, that's a very good observation. So right. So this 2, do we see why this 2 is not a bottleneck edge? Does anyone have a question in chat about that? That's a very, very good point. Okay, so what else is not a bottleneck edge? This 3 actually is not a bottleneck edge either, for the same reason. Okay, why is this 3 not a bottleneck edge? For the same reason that this 2 is not a bottleneck edge. Right? If we change this to 4, well, then this goes down to 1, and that comes out of this. Like you can't pump 2 units of flow, you can only pump 1. So changing 2 and 3 to like 3 and 4, for example, or just really anything, like 2 plus epsilon and 3 plus epsilon, doesn't do anything with max flow. Okay? And why is this? Well, it is true that in some sense, the bottleneck edges are related to the minimum cut. But the issue here is there are 2 minimum cuts. There's this one, okay? And then there's this one. Okay? So the edges cut in this first minimum cut are the 4, 2, 2, and 3 edges. The ones cut in like this diagonal cut are the 4, 2, and 5 edges. So what do the 2, sorry, what do this 4 and this 2 have that this 2, this 3, and this 5 don't? Not only are they part of this maximum cut, they're part of both maximum cuts. Minimum cuts. Okay? So this 4 is part of both of these minimum cuts. Why does this make sense? Well, what if you increase this thing over here, right? This is part of this top minimum cut over here. This 2 over here. So this 2 becomes a 1, let's say. Let's say 3, right? Let's say we increase this 2, right? Does the minimum cut of the graph go down? No, actually, because this cut over here, the diagonal cut, still maintains its value of 11. Okay? So you can increase the value of an edge in some maximum cut, or minimum cut, pardon me, without increasing the overall minimum cut of the graph. Okay? And that's because there could be some other minimum cut that does not contain this edge, and just changing that edge in a different minimum cut does not affect the overall global minimum cut of the graph. Okay? So we need, right? So the bottleneck here, the bottleneck edges are the edges that are part of all minimum cuts. Okay? Bottleneck edges are the ones that are part of all minimum cuts, because then increasing the capacity of those edges increases the capacity of the minimum cut of the graph, guaranteed. Okay? And you should convince yourself of that fact. My apologies for the confusion. Does chat have a question here? Okay, I guess not. So yeah, again, right? So this is exam prep, so I will reiterate this. One of the best ways to understand anything theoretical is to take the problem and change it a little, right? Like make some small modification of that problem and try to see how it changes. So what if you define the bottleneck edge as if you decrease it, then you decrease the capacity, or then you decrease the max flow in the graph. So this, for example, isn't a bottleneck in that sense, because if you change the 7 down to a 6, then it would still be, we would still be able to pump 4 units of flow, and then 2 units of flow down this path. But this thing over here, this 4, if you decreased it, then you wouldn't be able to pump 4 units of flow along this top path, you'd only be able to pump 3. So this 4, what does this 4 have that this 7 doesn't? Remember, I'll let you think about that problem. Okay, it's an interesting practice problem. Would you like me to go over it at some point, or would you like to just think about it like for a while, and then you can ask me if you have a question later? Huh?
Go over it.
You want me to go over it? Okay. So remember, do we understand the rationale for the original bottleneck, like being it has to be part of every min cut, right? Because raising an edge in some minimum cut doesn't guarantee that you raise the overall minimum cut, right? There could be just another minimum cut that doesn't even have that edge, and that value remains the same because you don't change anything there. However, if you decrease the value of that edge in any minimum cut, the minimum cut of the graph goes down, right? So this bottleneck, like this alternative bottleneck definition, I don't know what to call it, like bottleneck 2, I don't know. So in this alternative bottleneck definition, right? The solution is not that you are part of every minimum cut, but just that you are part of some minimum cut. Because you can decrease the capacity of any edge in that minimum cut, in any minimum cut, right? That cut decreases in value, and it becomes a new unique minimum cut. Okay? Does that make sense? Well, maybe not unique. Definitely not unique, but it definitely decreases the value of the minimum cut overall. Because you have a new cut with less value. Any questions about this? Yeah, I guess it's really important to understand like these conceptual questions. There's going to be a lot of them, probably on the test like last time, right? So I know you really have to understand the concepts quite well, and this strategy of changing things up and seeing how the problem behaves or reacts to these changes is a great practice to kind of get you used to just asking why, right? Why is this true? I think that's the best thing you can do for yourself while learning. Okay? Any questions about this?
So for the residual graph,
Very good question.
yeah. So for the residual graph, when we get like all minimum cuts, there's just a single edge that's facing the opposite way.
Yeah, I believe so. So
So that's how I found out for that other one. I just looked at there was another edge facing.
right. So like, yeah, this edge would be part of some minimum cut, right? So this one, and this one, and this one, this one, and then you just try to see how you can partition the vertices to get a cut involving only these edges. Okay, yeah. There's other ways you can recover the minimum cut, like more clever ways you can recover the minimum cut from just the 4-12% algorithm, but I don't think I want to go into those. I think you just look at the edges going backwards, and that's pretty much good enough. Okay, so I think now we're going to talk about dynamic programming. Okay, so any last questions about this?
But this is a clarify. So the only bottlenecks are AC and DC because they're part of like those minimum cuts. The other like the AD, BD, and DT aren't because they kind of like depending on the values of that either like 2 of them are part of them or only one of them is.
Yeah, so AC and BC, right, are part of every minimum cut. That is not true about AB. It is part of this first minimum cut, but not this second minimum cut.
Okay.
Okay. So right, so that's the solution there, and then, like I said, if you like define a bottleneck by if you decrease it, then the max min cut decreases, or max flow decreases, right? Then it's like if it's part of any minimum cut. Okay, so there's an interesting duality there. Okay, so we're going to talk about. I think we're going to talk about dynamic programming. So let's look at the chain matrix multiplication problem. Okay, so I think that's this first dynamic programming problem. I decided to choose this because I felt like the other one was somewhat similar to what we were doing already with string splicing and things like that. So that I would just direct you all to do that one by yourself. But I feel like chain matrix multiplication is like unique enough of a problem that it's worth talking about. Okay, so yeah, try to think. Remember that the 4 steps, right, are to define your subproblem, define your recurrence based on your subproblem. You know, like consider how you're going to fill out a table of subproblems, and then choose an element from that table, or combine the elements in some way, right? So like maybe pick the biggest one or something like that. Okay, so how does matrix multiplication work? Here's a quick refresher. The idea, right, is the ijth entry of the product matrix, okay, is going to be, you're going to combine this thing over here, this, like the ith row of the first matrix, and then you're going to combine it with this. So like this times this plus this times this, you're going to take the dot product of those vectors, and then that's going to be like the first row, first column, so it's going to be the first row and first column entry of your resultant matrix. Okay, and so how many operations does that take? So let's say this is like a m by n matrix, and this is an n by e matrix. So what are you doing, right? You're taking n elements and taking an n element dot product every time, right? So what is that equal to? How many operations are you performing? Well, you're multiplying and then you're adding them up. So that's an order of n operations. Okay? And how many times are you doing this? You're doing this MP times. Because there's going to be MP like final. That's going to be the cost, right? That the cost isn't too important, but you can define the cost in terms of the matrices. Okay? So the idea, right, is that if you matrix multiplication is associated. So ABC, you can write it as you multiply A and B first, and then you multiply that by C. Or you can write it as you multiply A by multiplying B and C first and then multiplying by A. So like what is the difference here, right? So if I multiply A and B, what do I get? That's the Wi-Fi. Okay, so if I multiply A and B, what do I get? It's 3 by 8 by 2. Okay, 3 by 8 by 2 is like, what is that? That's like 48. Okay, and then what do I get? I get a 3 by 2 matrix, right? And then it's 3 by 2 by 5, which is 30. Okay, so this is 48 plus 30 operations, which is 78 operations. However, if I parenthesize it BC first, then okay, 8 times 2 times 5, right? What is 8 times 2 times 5? It's 80. And then I have an 8 by 5 matrix, right? That results from that. And then I do a 3 times 8 times 5, which is 120. So this is 200 is much bigger than 78. So we realize that we need to multiply it like this first. So we don't have too much time, so I'll just like go over the solution to this. Let me erase this. Does anyone have any ideas for some problems? Any ideas? Okay,
There's a repair.
sorry.
I'm not sure, to be honest.
It's okay. So I mean, it's not very intuitive. So let's call this a problem C. So realize that like you have to okay. So let's think about this. So one idea, right, which turns out to be the winning idea, is to figure out how best to parenthetize matrices in a range, right? So for example, if I have like A, B, C, D, E, if I have these matrices, then the problem 1, 2, 3, 4, 5, the problem C, let's call it CM. The problem CM of 2, 4 is to figure out the best way to multiply these 4 and then do A and E after that. Okay, so it's to like you consider a subsequence. Cm of I of j is equal to the least, or fewest, I should say, the fewest operations needed to multiply sequence A sub I, A sub I plus 1, A sub j. Okay, so to multiply this contiguous sequence, what is the fewest number of operators here? Okay, so now does anyone have any ideas for how we can write a recurrence with this? So what is, so yeah, what are different ways we can parenthesize this, right? Like let's say we have a sequence of matrices here. So let's consider A of 1, 5, or CM of 1, 5, okay? We're gonna figure out how to parenthesize this, for example. What can we do? We can first parenthesize it like this, and then figure out how to parenthesize, like best optimize this subsequence. Okay, right? That's one option. So CM of 1, 5. One option is to figure out this first thing, and then like CM of 2, 5, right? That's one option. What is another option? We can try to figure out how to optimize this sequence. Well, I mean, it's a base case because there's no way you can parenthesize. You just have to end up multiplying them. then we can figure out how to do this sequence, right? So CM of, what is that now? CM of 1 to 2, as well as CM of 3 to 5, and so on and so forth. So the idea, right, is the recurrence is going to be based on where we draw this division. Okay, so where we put like some set of, like the outermost set of parentheses. Does that make sense? Okay, so CM I comma j is going to be equal to, right? We're going to minimize across all possible points we can put this. Okay, so we'll say we draw this at k. So where is the lowest point we can draw k? The lowest point we can draw k is just after I, and the farthest point we can draw k is just before k. Okay, so the minimum for k goes from I plus 1 to j minus 1. Honestly, I'll just write it like this. So k goes from I to j, but not inclusive. So in particular, k cannot equal I, because then you just get a cyclical dependence. Cm of I comma j will depend on Cm of I comma j, and we don't want that. So why does it keep doing that? Okay. Maybe I'm not moving around enough. Okay, so it's the minimum across points where you can draw this division. And so for any choice of k, what is the cost going to be here? Well, it's going to be the cost of multiplying the first half, so that's Cm of I comma k, right? And then you have to add to this Cm of k plus 1 comma j. Okay? And then you also have to add the cost to multiply the two resultants. Well, how do you determine the cost to multiply the two resultants? Well, realize that when you have like a chain matrix multiplication problem, to this thing over here, this 8 and the 8, they kind of like get absorbed into each other, and you're left with a 3 by 2 matrix. When you multiply this by a 2 by 5 matrix, it's 2 and the 2 kind of fold into each other, and you get a 3 by 5 matrix. The final result, right, is going to be the number of rows of your first matrix by the number of rows of your last matrix, right? So what you do is the cost to multiply the two results is going to be the number of rows of I, because it's the first matrix, right? So let's say this thing is like R1 by C1. Okay, let's say this one is R2 by C2. This one is R3 by C3. And this one is R5 by C5. What is the cost to multiply, once you multiply this section and this section, what is the cost to multiply the resultants? Well, this matrix is going to be what? What is its dimension going to be? A1 times A2. Exactly, it's going to be R1, C2, right? So we have an R1 by C2 matrix, and we're multiplying by, what is this? A3, A4, A5, what do we get? R3 by C5. Okay? We know for a fact that R3 equals C2. Right? Otherwise, the matrix would just, it's just not defined. Right? The number of rows of the next matrix is equal to the number of columns of the previous. So that's just what you need for matrix multiplication. Okay? So we'll say it's just C2 because we don't want to write too many variables. And then we have C5 because it's the last matrix, that's the number of columns. So the cost here is going to be R1, C2, P5. More generally, why is this 2? Well, that's where we grew K. That's what we chose for K, right? Why is this 5? Well, that's J. Why is this 1? Because that's I. So it's going to be like the number of rows of I times the number of columns of K, right? The K matrix times the number of columns of the N matrix, which is K. Okay, so this in some sense is dynamic programming plus divide and conquer. You're dividing it into these subproblems and conquering them by multiplying the results. What is the best way to divide and conquer? Well, the dynamic programming algorithm will tell us that. Okay? Does that make sense? So what we do is, right, we fill this out for each choice of I and j. So let's think about the runtime here. There's no morals today, really. I mean, it's exam prep is always didactic, but I think I would just recommend reading the exam tips I have. But let's analyze the runtime, okay? So how many subproblems are there? There's like any choice of I and j, right? J has to be greater than I. So there's like n times n minus 1 choices, okay? And for each one of these, how much work do we do? Well, we look at all k going between I and j, right? And so the time it takes to fill out each element of this table is dependent on the distance between I and j. Okay, does that make sense? So we can think of it in some sense like the average distance between I and j is like roughly n over 2, right? I mean, this is just asymptotics. So times something that's O of n over 2, and we get something that's O of n cubed. Why is this n over 2 again? Well, because you think of any I and j, and on average, I swear to God, on average they're like n over 2 apart, or some linear factor of 10.
Sorry, where did the n minus 1 part from?
But that's the number of choices for I and j.
Oh, okay.
So yeah, the table, right? Like 1, 2, 3, 1, 2, 3, 4. This is I, this is j, right? You realize, right? Like this is the table of the subproblems you're going to fill out. So 1 comma 1, it's like, okay, so 2 comma 1 doesn't make sense. Like this problem does not exist, right? Because I cannot be greater than k. But this problem also doesn't exist. This problem also doesn't exist, so on and so forth. Only this top triangle, in this top triangle, does the problem exist. In fact, for I equal to j is also like a base case. So you'll find that this is n times n minus 1 over 2, right?
What is it?
N is the number of matrices. We have matrices like I guess I used n here, but n is the number of matrices. Okay, so right, so what do we have here? Well, this how many different subcases do we check here? We check one subcase here because there's only one way to parenthetize right down the middle. Here with 1 to 3, there's 2 ways to parenthetize. Parenthetize like A1, A2, and then A2, A3. Those are 2 different ways to do it. So there's 2 here. 2 to 3, there's 1. 4 minus 2, there's 2 ways to do it. You do A2, A3, A3, A4. 4 and 3, there's 1 way to do it. 4 and 1, there's tons of different ways to do it. You can draw the line like here, here, or here, and then think about the subproblems from there. Okay, so there are 3 ways to do this, and the idea, right, is you add all these up, okay, and this is a bit of an exercise, but you'll find that it is equal to roughly 2. Okay, what you're doing is you're summing for I goes from 1 to n. You're summing from j goes from I n of j minus I. This is going to be roughly cubic n. It's a pattern that you should recognize. It appears very often in dynamic programming problems. Okay. Any questions here? Any questions from the chat? Okay, so if that's the case, I will stop the recording.